Okay, for these problems, I'm going to cheat a little bit in that I've already done them out. I did them out earlier and with the calculator during the lecture, and when I rewatched it, I watched myself punching numbers in for 5 straight minutes. So to save you that, I'm going to, it'll appear I'm going a lot faster than I should just working with the calculator. If that happens, just pause, but you really don't want to wait for me as I'm clicking away on the calculator. So here we are. We have 0.5 molar solution of cacodilic acid. It's a real acid. I found a list of the unusual ones online. And it has a pH of 1.09 at 25 degrees Celsius. What is the Ka for this acid? Well, so let's write out Ha plus water, and that Ha is this acid. You're free to write this entire thing if you want, but we're really only after that H+, and we know that that A stands for the counter ion. So it's up to you. If you wanted to do that on my exam, I'd be impressed. I'd be worried that you had wasted a lot of time writing that out. And this is the general form for any of these monoprotic acids. But it's up to you. Okay, so 0.5 is our initial concentration. None of this, minus x, plus x, plus x, 0.5 minus x. So some of our acid dissociates. The amount is x. We don't know what x is yet. We have x here, x here. Now, we need to put, well, first let's write out the Ka expression. We need to find Ka, so we're going to have to use this expression. And now that we know what we have at equilibrium, at least as far as the ratios here, we don't know what x is yet, but we know that we lose 1 x worth here, we gain it over here and here. So put these values in. Okay, now to find Ka, we need to know what x is. Alright, so they must give us the information, and they say the pH is 1.09. Well, we have the concentration of H3O+ is here, so x, I'm going to write it up here. X is equal to the concentration of H3O+. It's also equal to the concentration of A-, but we don't need that right now. And this concentration of H3O+, we learned earlier, is going to be 10 to the minus pH. And so that's equal to 10 to the minus 1.09, and that's going to be equal to 0.0831 molar. So that's X. So that's the concentration of A-, the concentration of H3O+, and then the concentration of HA is 0.5 minus 0.0813. Now, do they have that? No, they don't. Yeah, well, so we just put everything in right here, 0.0 squared, and then on the bottom we have 0.5 minus 0.0813. I think this comes up to be, we can finish it out before we do the final calculation. On the bottom it's going to be 0.4, so 419? Yeah, 419. Okay, and then that's equal to 0.0158. So that's our answer, the first answer that we need. That's our Ka. And then what's the degree of ionization? Well, the degree of ionization is the fraction of acid molecules that dissociated. Well, we know what we started with is 0.5. And then how many acid molecules dissociated? Well, that was X. And we learned that was 0.813 molar worth. So if we take X divided by the starting amount, that's the fraction that dissociated. So our degree of ionization is going to be X over the initial concentration of HA. We have to start with the full amount. This is how much dissociated, so the part divided by the total, that's going to give us a fraction. So this would be, we're doing it by concentration. We could do it by moles too, but since it's the same, the concentration of these species takes place in the same vessel, then it is it's moles per liter divided by moles per liter, and actually we could cancel the liters and we'd have moles over moles. Same fraction, but we have everything in concentration, so let's stick with that. And then we end up with 0.163. So the percent ionization and I believe that's mentioned in your book, that's just going to be equal to 16.3%. So the degree of ionization is what we are after. It's 0.163. But people like to see percentages, so you just move that decimal place over 2 places and use the percent sign to get the percent ionization. Either one. Okay, so that's one of them. Let's do the next one here. Alright, so now we have barbituric acid or barbituric acid, I don't know. But it's it's an acid that has a pH of 2. At this concentration it has this pH at 25 degrees Celsius. So it doesn't matter what it is, we'll call it HA. And you know, that's the thing, I don't even have to specify an acid. I just wanted to get one that was a real one, and I backtracked to the pH for it, knowing it's Ka, and so we're finding Ka here. But it's nice to have that. But I could have just said the this 0.450 molar solution of a certain acid. And that's all I would had to say. But I gave you one here, but we're still going to call it HA because it's just too long to write out. We have H3O plus, A minus. We're going to have that ice table again. And so, make sure I'm on here, we have 0.450 molar, 0, 0, minus X, plus X, plus X, 0.45 X and X, like we've seen before. The Ka expression, I'm going to write it out again, though after a while you should be able to skip this step, and I wouldn't mind that on my exam. Instead of putting this in, you just wrote this and then solved it. And then X is the concentration of H3O plus, which we know to be 10 to the minus pH. And they gave us the pH, it's minus, so that's 2.5. Yeah, 2.5. And this comes up to be, what is it here? 0.00316. Now, this pH here is a lot higher than the previous one, which means that it's a weaker acid. It did not dissociate as much. Now, it's a different concentration, but it's close. So to have that close of a concentration up here, and the pH is that much higher, we should expect that the degree of ionization is much lower. And you don't have to be thinking along that line. But it does help, especially if you come up with an answer that is obviously wrong. If you're thinking about it, you might pass over it if you're not. Okay, so this is 2.23 times 10 to the minus 5. That's a very small Ka compared to the one that we had before. And the degree of so that's our one answer. The degree of ionization then is going to be, it's really the concentration of A minus over the concentration of HA initially. So that's just X over the initial concentration of HA. This is 0.00316 divided by 0.45. And we get certain to put the molars in. Those are going to cancel, because the degree of ionization has to be a fraction, just a number. And this comes up to be 0.00702. That doesn't tell us as much as, or it doesn't tell me as much as putting it into terms of percent ionization, which would be 0.702%. So it's less than 1%. It's harder for me to, I mean, I can certainly figure it out, but it's harder for me to get information from this than from this. That's why we do convert to percentages. Okay, and that's it.